Good afternoon, everyone. Welcome to the session on civil engineering and renewable energy 2. My name is Miguel Nóbrega from the University of Minho in Portugal, and I'll be the chair for this session. The first speaker for the session will be Professor Rita Carvalho from the University of Coimbra. And the title of her presentation is Numerical Study of the Flow Transition in a Sewer Between Manholes. Please, Rita, go ahead.
Hello. Good afternoon. So I will present this work. This is experimental work, and this workshop I usually try to do something that I did not see. I did not have done before. So we are trying to simulate our installation here in the University of Coimbra. Okay, so the aim is to simulate free surface to pressurized flow occurring in a pipe between two manholes, and to preview the flow in our installation, dual drainage installation. And also to see if simplification in the domain are possible, and which implication have in the calculus, in the efforts, and as well as in the results. Okay, so I will present our installation. So we have a big channel and the main circuits in our labor, and this dual drainage was constructed after the previous one, and we provide from the main circuit. There is a reservoir downstairs and the reservoirs in the upper level, and we have 4 pumps to generate flow from the lower reservoir to the upper reservoir. And then here's the main circuit to the big flume here. And we can also derive the water for coming to this dual drainage installation. So if we close the valve for the main circuit, we can induce the water to go for the pipes between two manholes, or the other channel that is here and coming by gullies to the manholes and then going down again. So this installation, I will use just the pipe, the manholes, and the main circuit as is explained here. And the pipes are, that one has 300 centimeters diameter, and the others 350 and a half. Okay, so these are the two manholes. One is acrylic to see the flow inside, and the other is commercial one in plastic. This part has a detail that is a pipe here that the water goes in a half pipe inside the manhole. So this is the schema. Also, we have valves here in the circuit that we can manage automatically. So closing that one or that one, and then we induce some floods. Even the water can go from the manholes to the gully and to the channel that could be a street. Okay, and we have as well 3 discharge flow meters. That one, if we can operate this valve to have pressurized flow here, and that one, when we have free surface here, doesn't operate. And we have a mobile flow meter as well, and we include here in the manhole to see the results. We have also 8 pressure transducer in the bottom of the pipe here, and we can measure that. So first, in the preliminary results, we use simulation. We use INTERFORM, and we want to use also air INTERFORM to see the air entrapment in the pipe. Okay, so we did a block mesh with snappy mesh, doing all the geometry in Salome, and then we have the 2 manholes and the pipes in the mesh. If we use all the installation, we did some simulation here, the inlet, outlet, atmosphere, and all other walls. But then we want to see how we could some experience, and to not simulate all this pipe, we try to do a symmetry plan here, and then we move the outlet here. That is here the valve number 2. Okay, so this preliminary simulation, we try to use a empty and just the flow entering, but it's taking too long. So we start already in the half level in the pipe, and we try to do some sudden inflow, a sudden close downstream, sudden inflow and close downstream. And also we try to simulate as a dynamic mesh a valve closing to limit the flow. Okay, so this is the installation starts here. So as there is a lot of turbulence here, it's very difficult to have a nice time step. So here we have in other perspective. And then we try already in the half pipe, and we did sudden inflow in the pipe. Okay, and there is also here some air, and then it goes down. We did also a close here. So this is, we can change this outlet from a wall, and then we induce the also some inflow here, and we have a passage here. And if we know the pressure here in a point, we have a kind of that diagram. So these were the preliminary simulation. And then we looked at the installation. Finally, we could use that in the end of March. So we tried to do some simulation, and we can have about discharge flow from 16 to 58, and we can operate the valve 1 or the valve 2 or both, and to expect steady condition. Okay, so all the equipment, we can monitorize the valve. So we have the position here, and we can close if the valve is 50% open, we can close in less than 10 seconds, and then we can operate after also more than 10 seconds. These are the discharge flow localized in different position, and these are the 8 pressure gauge in the pipe, and we have some perturbation here. For the discharge from the water level, because we have a discharge flow that is, as I explained here, we have okay, sorry, we have we have a discharge flow that is pressurized, but the water is free surface, and the discharge flow meter doesn't work. So we use another discharge flow meter, and we could distinguish the position to synchronize with the others. About the 9 pressure gauges located in different places in the pipe between the manholes, we have different aspects of the pressure. So we'll try now to have the valve closed here, dynamic mesh, the valve 2. So we have here open, and if we turn around this valve, that become closed because it's studied to obturate all the pipe. So we want to turn around just a quarter to be closed in 10 seconds. That is the time when the valve is operating. I think that the preliminary simulation show that it's possible to simulate the transition from free surface to pressurized flow. We can have some simplification that could be good. The symmetry doesn't have a very impact in the results, but the valve operation, yes, and if we don't use that valve instead of that one, we can have a symmetry plan like this. And it's very important to have an accurate valve operation to have the real condition that we can compare the results from numerical with the experimental. Thank you.
So, thank you very much, Rita, for the nice presentation. We have time now for questions, and it seems no one typed the question. Maybe I can start, Rita, by asking you. You mentioned during your presentation solver. It's INTERFORM. Is it something that you are developing by yourself, or is that available on the public distribution of OpenFOAM?
It was a PhD student that developed in OpenFOAM 2.3.0, and then I tried to upgrade to ESI group to version 18. It works, but doesn't have the same results. And now I have the INTERFORM in version 5.0. So I would like to have some time to study why it doesn't work in as I wanted with the comparable results in the ESI group versions.
Okay. So I believe there are no more questions. We are on time for the next session. So thank you again, Rita, for the nice presentation. Oh, sorry, we have here a question.
Okay, let me say that I will present the last presentation with INTERFORM, and I will show some more details.
And the question we have here, Rita, is related to activities you have done with the simulations. Have you considered optimize the feasibility to reduce vortex generation and improve the fluid flow in your studies?
No, we try to do the experimental results, but we just have some short time, and we did some preliminary simulation, physical simulation to know what to do with the numerical, and to have the same simulation in physical experimentation and in the model. and we try to close and to operate all that valves to see what we can have. And now we are a PhD student will work on that to try to have the same operation, but it seems that the best way is to start in a steady state like half pipe, and then operate this valve.
Okay. Okay.
In a time.
Okay.
And this is spherical. That's why I try to include dynamic mesh.
Okay. Just to mention that you can use the chat and the other rooms in the discussion forum to proceed with discussion. I'm sorry, but we have to advance in order to fulfill the time plan. So we'll move to the second presentation of the session. It will be given by Mr. Cheang from UCD, University College of Dublin. And the title of his presentation is Validation of a 3D Computational Fluid Dynamics Model and Wind Tunnel Test Results for the Queen's Ferry Crossing, Mesh Sensitivity and Domain Study. Please go ahead.
Hello everyone, welcome to my presentation. My name is Cheang and I'm from UCD. So, long-span bridges are vulnerable to the effect of wind. The study of bridge aerodynamics is essential in ensuring the safety and acceptable performance. Typically, there are three methods used for the bridge aerodynamic design. They are field test, wind tunnel test, and CFD simulations. For the field test, it is reliable, but in the meantime, it is extremely time-consuming, and the sensors installed on the bridge are very expensive. The detection may also affect by the traffic or animal, etc. Also, is impossible to imply for the bridge design stage. As for the wind tunnel test, it is used for a very long time by the industry, and it's a common way for engineers to get relatively trustable results. It's reliable for most cases, but since the limitation of the size of the testing facility, the wind tunnel test is using a scaled model. So it's totally different from the real bridge condition. Even so, the wind tunnel tests are not cheap at all, and the issues like Reynolds number inconsistency, instrument interference, and so on could also affect the results accuracy. Compared to those two methods, CFD simulations are much more flexible. Firstly, you have the control of the level of accuracy and cost. It depends on the different purpose of your work. You can work on different schemes for the different level of accuracy. Secondly, in wind tunnel test, experimental results are normally collected from limited sampling points. If you need information of a certain point that is not sampled, you need to either repeat the test or interpolate the data from other sampling points. Well, in CFD simulations, you can extract information from all the cells within the domain. And CFD, it's non-intrusive, so there's no sensors, no interference. Validation is very important for the CFD simulations because the poor configurations can lead to unphysical results. Then let me give you a brief introduction of the Queen's Ferry Bridge. The Queen's Ferry Crossing Bridge connects the traffic between Edinburgh and Fife. It used to be the longest three-tower cable-stayed bridge in the world. The bridge carries about 24 million vehicle journeys a year, so it's very much a major traffic connection. The simulations are based on this bridge, and I want to thank Arab and Jacob therefore kindly share the internal test report with us. So here is the geometry of my simulation. It is a 1/4 scaled 3D model with a bus and truck sample on it. It's created in AutoCAD and exported to STL files so that it can work in OpenFOAM. Since the location of the Queen's Ferry Crossing Bridge is an area prevailing southwesterly winds, in the winter test, we have tested the model with the other 3 different yield angles. So therefore, I get the configurations based on it, as you can see in the figures. The wind tunnel test is performed in a closed circle wind tunnel. It got a size of 36 long, 40 meter wide, and 4 meter high. I built a smaller domain to save some computational power. Simulation results have shown that the flow can fully develop in this scale. So I will talk about the domain study later. Let's move on to my mesh scheme. I work on 3 different kind of mesh schemes. Generally, it's a coarse mesh and a medium mesh and a fine mesh. Here in this slide, I'm introducing the best one of them, fine mesh. So the meshing procedure begins with generating the background mesh. I created 12,800 cubic cells of 0.25 meters weights, as shown in the figure. So the area close to the bridge model are refined to level 5, which brings the size of cell to 0.00625 meter. And the area around vehicle is further refined to level 7. Also, I set 7 buffer layers between adjacent levels to make the cell size changing smoothly. As the boundary layer's thickness varies with the flow conditions, the Y+ value is mainly considered as a reference for the quality of the mesh scheme. To make the simulation accurate enough, the goal is to try to achieve the Y+ value less than 1. So I added 7 layers of cells with an expansion ratio of 1.2 to resolve the boundary layers. The overall thickness of the boundary layer is 0.0005 meter, which is close to the dimension of the level 7 cells. And overall, there are no distorted cells. The average non-orthogonality is 7 degrees. The maximum skewness is below 4. So, and the Y+ value of the bridge surface is less than 1. So it's a good mesh, and the total cell number is around 100 million. Here is a summary of the 3 kind of different meshes. Generally, they're different in the level of the refinement. And the fine mesh got the best refinement of the bridge. The coarse one got a lot of part of the bridge broken or distorted. So it's a main reason for the inaccuracy, and you can see that the Y+ value, the fine one, is the best one. It got average Y+ value of 4. The wind velocity is, as for the boundary condition, the wind velocity is 4 meters per second, and turbulence mixing length is 0.7. This two is exactly same as the wind tunnel report, and the value of K and omega is calculated by these 2 equations for the initial value, and it will be calculated by the transport equation. K value and the K value of the bridge surface is said to be very small instead of 0, because it's to try to avoid float point problem. Aerodynamic force acting on the vehicle are recorded and then calculated by the equation I showed here, which is provided by the wind tunnel report. So the figures show the results comparison between the wind tunnel and the safety results. We can see that the main difference of the results are shown on lift coefficients. here is a big difference, and for the drag coefficients, it's small different, and they are similar. The percentage difference, the different percentage between the two can be more than 180%, which happens here, the coarse mesh and the blue one, internal. So generally, the average different percentage of the fan mesh is only 14. And for the medium chaos one is 24 and 35. So the results indicate that the fan mesh scheme is the best one, and it's necessary to use that. A large domain and a full domain, which is exactly same as the internal domain size I investigated. Domain 1 is the domain that I used in the previous studies. Domain 2 is a larger one, which has a size of 20 meters long, 7 meters wide, and 4 meters high. Domain 3 is exactly same as the internal. So all the 3 studies were applied to the geometry of zero yaw angle and the mesh schemes and all the other parameters of the fan mesh I used. Results in figure AC shows that the drag coefficients are similar. However, from the lift coefficient here, we can see that the results show different, and it needs more mesh refinement for the larger domain, because it uses a lot of power on the background mesh. So we can see that when the turbulence can fully developed, the domain size used in the modeling was not significantly affect the simulation results. So it's okay to reduce the size of the domain to considering the need to be efficient with the computation powers. Here is the sliced flow visualization of the domain 1 simulation. You can see that here, the turbulence is fully developed. So basically that's all. Thank you for your listening and thank you for your time. Please be free to ask me any questions.
Thank you, Cheang, for the nice presentation. We have already a question from one of the attendees. First of all, an excellent work. And the Y+ plot on the breeze surface looks fantastic. But the question is, how long did the simulations take to converge? I believe you shown a slide where you show the differences in terms of computational time for the coarse and the refined mesh in comparison with the reference one, but I believe you didn't provide the actual times. And this is the question: how long it take to converge? Okay. For instance, the reference mesh you have presented.
Okay, thank you. That's a good question, and it's different for the one I showed in the picture. That one, it takes me like almost 4 days to converge because I use 120 cores because the number of cells is really huge, so it takes a long time. And for the others with different yaw angles, and the yaw angles leads to the different number of cells, so it takes even more longer because the cell number is a lot more than the zero yaw angle one. So on the average, like it takes 4 days to
4 days
for each simulations.
Okay, that's nice. Thank you.
Thank you.
So I believe there are no other questions, and we are on time to finish the. Sorry, we have another question. Have you used K-Omega SST model?
Yeah.
Is that the model I've used?
Yeah.
why have you used the model? Which were the motivations to use it? And the other question, just to finish, is how they compare with the other turbulence models?
Yeah, I didn't compare it in this study, because in this study I want to use the K omega SST because it's like a better one. I used the K epsilon one to compare it with it, but it's not as good as this one. So in this study, I just use K omega SST.
Okay, okay. So thank you for the clarifications. Thank you for the questions, and we're on time to move for the next presentation that will be given by Professor Javier Lara from Fundación IH Cantabria. And the title of his presentation is Extension of the Overset Mesh Method for Modeling Geophysical Flows and Maritime Applications. Please, Javier, go ahead.
Thank you, Miguel. Hello, everybody. Thanks for coming to this presentation today. So this is a team of has been performed the simulations and the work, which is formed by Alessandro Romano, which is a senior researcher, and Gabriel Barajas, which is a senior CFD developer, and Inigo Lozada, which is full professor of our institute. So this is the outline of my presentation. Then I will start with some motivation, then I will go for some objectives, then I will tell you about the method, then I will show you some validation and some concluding remarks. Let's start with the motivation. So the motivation we have is that we have different types of, let's say, problems dealing with waves and structure interaction, in which we could find two types, let's say two typologies. One could be related with the fact that they are fixed structures, so the fluid is moving around. And the other one, what we have is moving structures, in which there could be some cases in which indeed the motion of the structures is developing a very large motion. So in that circumstances, what we would like to do is to develop a method, or to find a method which is good to study how is the flow generated, how is the flow influenced by this large motion of the structures. And we have two options. One is inverse boundary method and overset method. The inverse boundary method is the one we are not following in this study, because we would like to use a body-fitted approach, which is able to predict or to simulate what we have all around the object where they are moving. And what we have here is the overset method, which is another possibility that we find in literature, in which the flow around the object is very well defined according to the definition of a body-fitted mesh. So how the model is working is this approach is working is very easy, due to the fact that what we can do is to define a fine mesh which is surrounding the object, and we have a background mesh which is containing the whole of it defining, which is used to solve the rest of the domain. Here we have an object, an example of a buoy which is floating on the water, and then we have the definition of the fine mesh which is on top of the background mesh, and then we can easily see there is no interference between the two meshes. There is a connection. We have an interpolation method which is working between both meshes and is transferring information from the, let's say, the coarser grid size or mesh to the finer mesh. So we using this method for problems like the one you can see here, which is landslide generated tsunamis. I'm a civil engineer, and we are very much interested about the waves that a tsunami landslide could generate. They are generating transient effects that are called tsunamis, and these tsunamis can be submerged created by the submerged landslide, as the one you can see in this picture, or the one you can see in this video, in which we have an emerged landslide which is producing this tsunami wave. So in this, it is really, really important, because we have found these kind of problems in nature, and there have been some of them. You could perhaps remember the one occurred in 2018 in Indonesia, but there are several examples that are creating dramatic effects on the coastline, and we are very much interested about that. So there are several examples of numerical study that has performed similar analysis, and we could find several, let's say, approaches, something like using structure and structure meshes, or even meshless methods, but most of them are simulating a landslide without a proper definition of the momentum flow exchange around the moving object. So the objective we have in this project is the one you can see here. We want to extend the overset method to consider the landslide problem, and we would like to extend the philosophy of the use of the overset method, which is basically used for floating objects in which there is no interaction of the background mesh with the boundaries or with even another solid object, to extend this methodology to have to solve problems where there's a large interaction with other solid, in this case sliding of let's say some object over a fixed solid body. So the method we are using was developed and was presented in this paper, and is using one approach in which we are using two types of equations which are coupled. We have developed these porous media flow equations that are used in our civil engineering problems, where we have a rubble membrane water problem in which the water is penetrating through the porous region, and we are using this method that couples what we call clear fluid region, in which there is only water, with a porous flow region in which there is a porous media flow. So the overset method will work here in between, in which part of the domain of the overset domain will include a porous media region and the other will include the clear fluid region. So then we can in somehow consider the solid where the landslide is working as a solid, not really a solid, but with a low permeability medium. So this method was developed by Romano in 2020, and it was tested with providing very good results. You can see here some examples about the mesh and the geometry we used. And the more important thing is that we developed an analysis of the flow within the porous media region, and we discovered that according to the low permeability media as it was defined, the velocity on the media was very, very low. So we will consider that this media, even is defined as a porous media, could be considered as an impermeable one. So the goal of this project was to enlarge this validation for aerated landslide. So the landslide starts in the air part and then is translated into the water to create a tsunami wave. So we tested our model to be compared with experiments that were developed in Italy by a consortium of 5 universities. And the idea was to simulate something similar to Stromboli Island, which is a big risk of landslide problems. And then they were developed this very high detailed analysis of wave run-up all along this conical island. And also they had several wave gauges that were rotated with this element, with this device all along the island to get a proper definition of the wave evolution along the island. So this is an example about the simulations. This is an example about the data. What we have 5 millimeters cells is the smaller cell size. We used 33 millions of cells. It takes 14 days to finish to complete the simulations in 128 cores. So you can find here some results of the simulations in which you could find how the object is moving all around. You will see the difference between the two meshes. We plot it in this way to show you the difference between the two meshes and how the model is able to capture the three-dimensional flow characteristics, especially the waves which are being produced, which are traveling all around the island, which is the more difficult part to predict, which is very important to assess the risk of flooding due to these tsunami waves. So let me show you some results about the validation. The validation is done with all these meshes. All the dot points represent the location of the free surface gauges, and we have picked only 4 in 2 transects. And here we have this blue line represents the ones which are in 10-degree line, and this green line represents the ones which are in 25 green line transect. And you can see how this is the more inshore location, these are the more offshore location. You will realize how is the performance of the model, which is able to capture this transient effect quite with a very good accuracy, considering even capturing the amplitude of the waves and also the phase of the waves. So the period is also very well captured, and you can see how it's able to simulate also how the waves dissipate while they are moving in an offshore locations, due to the fact that this element is radiating energy to other parts of the numerical domain. So let me go for some concluding remarks. So what we have done here is to develop and increase the capabilities of the overshed mesh technique, which has been including to interact with to be able to get interaction between two solid objects. One is defined as a porous flow, a porous media, which is able to reproduce, and this method is able to reproduce the landslide problem that can be used to study tsunami waves generated by these kind of features. So the model has been run has been validated with some experimental benchmark database, and we have a very good agreement that now we are doing is to extend this validation to simulate or to be able to check if the model is able to capture not only the waves which are really, generated by the tsunami, by the landslide itself, but also how are the waves propagating all around the conic island, producing different wave run-up all along the island. So thank you.
Thank you. Thank you very much, Javier, for the very nice presentation. So we have already some questions. First of all, excellent work. Congratulations. Why did you consider a low permeability region and not a fluid-solid interaction simulation?
Well, the reason of doing that is because the method itself is not prepared for the interaction of two solids. So the overshed method is able only was developed for floating objects. So there is no interactions of the mesh when there is moving all around the domain is not interacting with the boundaries or with another solid. So the reason to do that is to use this technique because we want to get a very good reproduction of the momentum exchange between the motion of the object and the surrounding fluid, and at the same time we would like to preserve the use of this to preserve the location of the slope. In this case is modeled by a porous media flow.
Mm-hmm. Another question from the audience. Amazing work. And the person is asking about the OpenFOAM version you have used. And the
we are using the ESI, the last version. Okay, so we have developed the porous media flow for that. Indeed, the version, I mean, this is working with the previous one because the porous media flow model was developed 2 years ago. So we have been updating the code for that. And then, the overshed method is developed for the new one, which is the one which is already available on the ESI. So this is really updated, as well.
Okay, thank you. And another question is related to, or is asking more details about the methodology to select the time steps in the simulations. What do you do?
So the simulations, the time step is 10 power to -5, 10 power to -6. It depends on the motion of the object. At the very beginning, while the object is running down the slope, the time step is much lower. Then it's increasing because there is no motion of the overshed method. It's only just motion of the fluid in the surrounding and is generating the wave. So the smaller is 10 to the power -6, -5, -6. Yeah.
Mm-hmm. Okay, we still have another question, and for the floating structure in 6 degrees of freedom, complex one. How do you calculate the moment of inertia, orientation, center of rotation for the overset mesh dictionary?
They are provided by the object and the model. OpenFOAM model is referring to this, so it's correcting automatically. But this is an input, so we get it from laboratory experiments and from laboratory measurements on some specification of the device itself. So this is something that is really defined at the beginning of when you're setting up the simulations.
Okay, perfect. Thank you for the questions. And we are just on time to move to the last presentation of the section. Of the session. Thank you, Javier, again. So we have again Professor RITA Carvalho from the University of Coimbra. And this last talk, or the second talk by RITA, is entitled Numerical Study of the Flow into a Pool Induced by a Vertical Jet. So RITA, please go ahead.
Okay, hi again. So it's another work that we tried to compare some different solvers to do a work that is very well documented, the pressure and all the work. That work was done in EPFL. Okay. Okay, and we have detailed data about velocity and pressure, and we want to analyze that comparing different solvers like the INTERFORM, INTERFORM, MULTIPHASE OpenFOAM. So the work in EPFL is well documented in several papers. One is that one in experimental in fluids, and this installation have a pipe here. And the jet goes vertical to the pool that can have several levels depending of these boxes that we can put different levels, and after the box there are some pipes that are the outlet, and here are also some space between the slabs in the plunge pool to know the pressure. We try to do INTERFORM. INTERFORM is well known, so the continuity momentum equation as well as the Wolff equation. We include the turbulence model. We use K omega SST because we want to look at the pressure near the slab. The multiphase OpenFOAM solves a set of equation, continuity and momentum for each fluid, and we use the solver in ESI that is available, and with this, the free surface calculation is not included because we have different phases that that interact and mixed, and each cell have their own percentage of fluid. So the air is better described. We can add also other terms as drag and lift and so on. And we also use the air INTERFORM that I presented before. That is a solver that is a subgrid model developed by Lopes Zeol, that is a PhD student of University of Coimbra. And with this equation, we have another equation for alpha G, that is the air. And we have here a source term and the velocity that can be different from air and water, depending of the interaction and the couple. So with this model, we have to calculate the source of air entrainment. So we have to calculate the position and also the surface thickness and perturbation. And following my work, we try to define different A with the K, depending on the K or K epsilon or K omega. We also have to calculate the velocity of the gas, the air in that case, and we follow some expression that are available also in the literature. So we we simulate, we did different simulation. We include all, but then to have a better performance of the solvers, we include just the same geometry, but the block mesh could be shorter, just this quarter. When we include the outlet here to catch this part, that part is finer, the mesh, and the atmosphere, inlet, and the walls. Okay, and then we have the mesh like this. First, we try this symmetry just in one plane, and then we saw that plane is also symmetric, and we do just a quarter. Okay, so we have different boundaries if we include a symmetry here or two symmetries here. The initial condition depends from the level, so we have different geometry. This is just 0.2 meters, but we have other geometry and then other meshes for each level of the pool. I'm sorry, I was saying that my backup broke down this weekend, so I lost the film. So I tried to do the film of INTERFORM that run between 0 and 10 seconds. So the jet came down, touch here, and then start to be different level, but the conditions are more or less the same. And we have a pressure here, and this is omega. The others are less, but we are looking at the pressure near slab in that line. Okay. So the air interfoam also run. Here I want to show that is not just the velocity of the water, but we include the other phase, and we can see here some air that is not described by INTERFORM. Here we have, here we see some air here in the first moment. And we can see that in INTERFORM we have some walls of that is not air, all this part, but here are more dissolver and is described better. If we look at the pressure, air INTERFORM has some different here. With the INTERFORM we have just a line here. Okay. So this is the multi-phase other foam. It takes much more time. Here we have also, like INTERFORM, that's parts, but we have a different condition from the INTERFORM. If we look to the pressure at the same time, we have here the multi-phase like INTERFORM, but some other value here that is not here. If we compare in a lower time, we have also some difference in the three solvers. So the pressure is not exactly the same, but is similar. But the difference are in the description of the jet falling and mixing in the pool. Okay, there's a negative part here as well. So simulation of the jet can be described by different solvers. The air entrainment just can be described in a realistic way, just in air interfoam and multi-phase other foam. The inclusion of the air in the two solvers air or multiphase INTERFORM, induced pressure profiles containing negative values which are not seen with INTERFORM in that experience. Of course, this has to be, we have to do more research on that part, but with this installation, with the very detailed pressure information, we can look at the difference in a better way. Thank you.
Thank you, Rita, again for the very nice presentation. So we have already a question from the audience, Leonardo Miranda. And the question is, could this solver, is referring to air interfoam, help us to study cavitation? An additional observation, he mentions that he figured out that he could capture better the air, the presence of air. So
we tried the air interfoam in step spillways, in jets, and with my first presentation with the pipe, I want to look at that. I'm not sure, but if the bubbles inside the pipes that we see in experimental installation that stay there, and sometimes they are very difficult to let the bubbles go out. I don't know if it is described exactly that now the PhD student will look at that. But of course, it's take into account the air, so I think that could be better than INTERFORM.
Mm-hmm. And also to study the cavitation problems. Yeah. Okay. Thank you very much, Rita. Another question is related to the models you have used. So you started by using half of the geometry, 1/4 of the geometry. Is the geometry axisymmetric? Is there any chance to use just one slice with a wedge boundary condition? Or?
No, because of the outlet. Mm-hmm. Yeah, that was my first thought, that we could just an edge, but the outlet is not, it's in the corner, so we cannot do that.
I see. So there's no chance to assume it is axisymmetric.
No, the last domain is 1/4. Mm-hmm.
Okay. And regarding the transport equation you have for the phase, there was a source term there. Are you using it for a specific purpose?
Yes, to calculate the air that can go into the water.
Mm-hmm. So that's the where you add the contribution of the source term in the equation. Mm-hmm. Okay.
Yeah.
Okay. Very nice. Thank you, Rita, again. I believe there are no further questions. I obviously recommend you to proceed with the discussions in the meeting hub and in the chat. Please interact with the speakers, with the other persons. There are a lot of tools available in the app to allow us to interact. Please do it. Thank you everyone for attending the session. And finally, thank you, Greg, for the support. It was very helpful, and the session ran very smoothly. Thank you, everyone. Looking forward to see you, hopefully alive, as soon as possible. Okay. Thank you.
Thank you.
Bye-bye.
Bye.
Bye, guys.
Bye.